Tango Delta.
Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the sands of past life.
NASA-in Istraživački centar Langley u Hamptonu u saveznoj državi Virginiji, jedan od prvih centara za istraživanje i razvoj u SAD-u. Obuhvaća gotovo 200 objekata na površini od 310 hektara. Zapošljava više od 3000 državnih službenika i vanjskih suradnika koji svojim projektima unose revolucionarne promjene u područje zrakoplovstva, šire spoznao zemljinoj atmosferi te projektiraju i konstruiraju tehnologiju za istraživanje svemira.
I'm a research scientist. I study the atmosphere and climate science, and really how we can learn about Earth's climate using satellite measurements. Right now, I'm the project scientist of a mission called Clario Pathfinder. And this mission is an Earth-observing satellite project that uses reflected sunlight, but we're going to take these measurements from the International Space Station.
The agency has subject matter experts across the various centers, a few dozen, not a whole lot of them, and I'm the one for interdescent and landing. I'm what's called a senior technologist.
I'm the 14 by 22 foot subsonic tunnel facility manager. My job is mainly to coordinate tests into the facility, making sure things run smoothly. We have a full schedule at the facility up to all the way to 2025.
As part of the Advanced Air Mobility Project, I'm the Deputy Project Manager for Technology. The Advanced Air Mobility Project is an activity integrating various technologies from across the agency to enable advanced air mobility.
As Center Director, my role is to serve the people coming through this gate, to create an environment where they can be amazing, to remove the obstacles, to help guide them through some of those obstacles, to tell them when we have to deal with that obstacle, to have that joy, because everybody's coming here for the excitement of our mission.
Mnogi članovi NASA-inih stručnih timova ovdje su već desetljećima. S mnogo strasti govore o svom poslu i radnom iskustvu, ali nisu svi tradicionalnim putem postali istraživači svemira.
I grew up in the 60s. My inspiration was Neil Armstrong landing on the moon. I was really good at mathematics growing up. We didn't have a lot of money, so I had to pay my own education. So I went to the public school, and the public university, NC State University, had aerospace engineering. So since I was, a big fan of Neil Armstrong, but afraid of heights, I knew I'd never be an astronaut, so I would try to instead to be an aerospace engineer. And so it turned out they had a program with NASA where I got a grant to get my master's and my PhD. I ended up with the aerothermodynamics branch here at NASA Langley. Working with them, I developed flow field codes to calculate the shock layers around these vehicles. And then ultimately I got involved in our planetary entry work, where we were developing understanding of how the vehicles going through atmospheres behaved. So I worked on Mars missions and missions where we were bringing samples back to Earth.
I actually joined NASA in my early 30s. After having spent a brief time in the military, I worked as a recording engineer, and I also repaired pinball machines and video games. So one day while tying down a pinball machine on the back of a pickup truck in the middle of a blizzard, I decided I should return to school. And I was much more motivated than when I went right out of high school. But when I got here, we did the traditional interview, and they took me on a tour. So we went to an environmental test lab, and they were taking an instrument through thermal vac, and basically it's a big giant 8 foot by 15 foot cylinder, and there's data being recorded, and you watch that data for 10 to 14 days. The excitement and energy of the people outside watching that, because their baby was about to go fly, it was all NASA. Everything else disappeared from me from that moment forward. So that's my path to NASA. Not traditional, but once it was in, it was in.
In college, I studied aerospace engineering. That's something that always was a passion of mine, so it was natural. Somewhat shockingly to me, I've been here almost 40 years. I've worked in my career mainly in the area of guidance and controls for aircraft and advanced automation with a variety of activities, looking at making aircraft simpler and safer to use.
My graduate education was spent studying the information in reflected sunlight and what we could learn about climate change from that information. And I started working on this project as a grad student called Clario. My interest in the atmosphere began with actually an interest in weather, rather a fear of thunderstorms. As a kid, every time a storm rolled through the region, now I lived in central Virginia, keep that in mind, I wanted to turn the Weather Channel on to make sure we weren't going to be run over by a tornado. I was intrigued by the meteorologists on TV and how they talked about putting the different layers of information together to construct the story that is a weather forecast. I ended up going to college to study more about weather, more about the atmosphere, and I realized, okay, I don't want to be a weather forecaster. That's not exactly what I want to do all the time, but I'm still intrigued by the atmosphere. So just continuing to explore through internships and talking to professors and talking to professionals, I discovered remote sensing. And remote sensing is just learning about something without touching it. So many of us use remote sensing in our daily lives with our eyes, with our ears. We're learning about the world around us, even if we're not touching every single thing. I thought it was magical that we could learn about ocean currents, that we could learn about clouds, all from hundreds of miles above the Earth's surface from satellite.
Well, I was interested in being an astronaut way back when I was a little kid in elementary school. Once I got into college, I applied to work at NASA. Actually, during high school, I came out to work at NASA. When I graduated from Virginia Tech, I got a chance to work at a wind tunnel. Hopefully, after working for several years at NASA, I could apply to be an astronaut, which I did in 1984, and got to the final 1,000 out of 4,000 people that applied to be an astronaut candidate.
U centru Langley trenutačno rade na solarnoj tehnologiji koja bi omogućila ljudima da žive i rade na mjesecu, a jednoga dana i na Marsu.
The first area is returning to the lunar surface to live and work. So we develop technologies, we have expertise in structures and materials, we have expertise in landing technologies, so we will be a part of that. And the reason that's special is because as we learn to live and work on the lunar surface, for us at NASA, it's a precursor to going on to Mars and deeper into the solar system. For the nation and for the world, it's an economic engine. Because just like I don't build an airplane when I want to fly somewhere, I buy a ticket. We want people to be able to buy a ticket to go into space. Today, Blue Origin did their demonstration flight with passengers. That should be commonplace, just like breakfast in Seattle, dinner in Washington, D.C. in the same day. We don't give it a second thought. So we are working on the technologies that will enable us to live and work on the lunar surface. And that's not in the distant future. We're working with private companies to inject our technologies so that we can explore and understand what it means to live and work at the south pole of the moon, or what it means to pull the ice from it so we can get fuel and oxygen.
When we landed on the moon, we used retropropulsion. There was no atmosphere at the moon, and so we had to slow down to land by firing rockets into the direction we were going. That served as our brakes. But when we brought the astronauts back to Earth, where we have this nice, big, fluffy atmosphere, we used that to decelerate us. And we came in a capsule, something called an aeroshell. And that has a heat shield on it because the temperatures you hit are very high. I mean, you're coming back from the moon, you're going 11 kilometers a second. And you have to dissipate all that energy, and that's in the form of heat and drag. So the heat, you have to protect yourself with a heat shield. That's the approach we use now. Any place with an atmosphere, we try to make use of the atmosphere. If we had not done that with Apollo, we would have had to carry fuel all the way to the moon and then brought it all the way back just to use it to decelerate us. And so we'd like to not carry the fuel anywhere we go, especially not for round trips.
So there are different types of remote sensing instruments, or different ways to use radiation and light as it passes through something like Earth's atmosphere. For reflected sunlight, it's kind of similar to, our eyes. We're using light to figure out how bright or dark something is, to assess the color of what it is. We can design instruments kind of in a similar way that can also measure the brightness and darkness of a scene, and then can also help us to break that light into its different components, kind of like a prism, creating something that looks a bit like a rainbow. You can also have things like LiDARs or radars where you're emitting a signal and then seeing how long it takes for it to get back, seeing how the signal has changed once it comes back to the sensor. The instrument will be mainly focusing on Earth. We'll also be able to point the instrument at the sun and at the moon to take some measurements there as well.
So the 14 by 22 foot subsonic tunnel is one of 15 major wind tunnel facilities here at the NASA Langley Research Center. They can range from a slight breeze to 10 times the speed of sound, or over 7,500 miles an hour. Our top speed is 235 miles an hour. Most of the things that we test in our facility is for takeoff and landing performance of various types of vehicles, such as airplanes, helicopters, launch vehicles, and sometimes we test odd things like wheelchairs, NASCARs, Indy racers.
The devices behind me were set up in what's called the cockpit motion facility. It's an area where we have research flight simulators to develop and validate advanced technologies before they go into a flight environment. The cabs that you're seeing behind me are different cockpits that can be used for different purposes. IFD behind me, the integration flight deck, it is set up to very closely match a current transport aircraft, 737-800. Off to my left side is the RFD, which is the research flight deck, to program up more flexible prototypes. We've been using it in the Advanced Air Mobility Program to look at these eVTOL vehicles that have barely just started to fly, and be able to prototype different flight control concepts and flight displays with simulated operations in urban areas.
Entry, descent, and landing is talking about that hypersonic entry, where we're coming in at more than 5 times the speed of sound, in fact, 30 and 40 times the speed of sound. And then we do a supersonic descent. So that's where you're kind of transitioning from that high energy environment down to subsonic conditions, where we can deploy parachutes like Apollo did, specifically about Mars. That is a big challenge for us because it has a very thin atmosphere. It's what I often call a poor excuse for an atmosphere. It's really too thick to ignore. We can't land there like we did on the moon without some kind of heat shield anyway, even if we did it propulsively. We can't land on it like Earth because the atmosphere is just not that thick. It's like 1% of the Earth's atmosphere. So at what was Mars sea level, we're at 1% of Earth. So we're at like 100,000 feet. So if you go to 100,000 feet at Earth, you feel like you're in space. You can see the curvature of the Earth. That's the densities we're working with.
Kao jedan od prvih NASA-inih centara, Langley je predvodnik na području inovativne tehnologije i istraživanja svemira.
When we were learning to fly, and that's the history of Langley Research Center, it made good sense to understand the atmosphere. So that's the core of our understanding Earth. So we have Earth scientists here. We have instrument developers here. So we put instruments up in orbit. We put them on airplanes. We put them on the ground. And we focus on climate Although we do build instruments, NASA, for NOAA, our colleagues that focus on weather, we focus on climate, which has a very long time scale. So we want to give knowledge to policymakers so they can make those decisions.
We all have temperatures. Everything in the room around me has a temperature. If we were to turn off the lights and we had something like night vision goggles on, we could use the temperature of the objects around us to learn about them. That's another form of passive remote sensing. We have instruments that are like that also look at the Earth. They can tell us, are these clouds really cold? So are they higher up in the atmosphere? Are they warmer, so they're closer to the surface? Are we looking at a colder or a warmer surface? And we can learn about some other properties of different corners of Earth's system as well, with these different types of radiation.
We started this new effort to develop what we call the hypersonic inflatable aerodynamic decelerator, another word for an aeroshell, and it's an inflatable aeroshell. So we deploy it, we have it stowed inside a launch vehicle, and we can deploy it before we enter the atmosphere, and we can make it a larger area than can fit inside the launch vehicle shroud. Right now, we're limited to the size of aeroshells that we can fly. We have to fit inside the launch vehicle shroud. And so that hypersonic inflatable aerodynamic decelerator, HIAD, was first considered in its infancy back in the 60s. With recent developments in high temperature fibers and fabrics and composites and stuff, now we can actually come up with a system that it's large enough that it decelerates higher in the atmosphere, encountering fewer and fewer molecules, so you heat up less. And so that combination of higher deceleration with lower heat rates and the ability to stow this means we actually have a system that closes. We can actually build a system large enough to get us to low enough temperatures that it will survive.
We have 3 sub-projects. One is called the National Campaign. It involves a large flight demonstration and test activity working collaboratively with industry and the FAA, doing a series of operational demonstrations to showcase where the current state of the art of the technology is, as well as intended to show the broader community what the benefits of this emerging concept advanced air mobility is. Sub-projects under AAM, one is called Automated Flight and Contingency Management. It looks at the automation onboard the aircraft, intended to make flying simpler and easier than it is today, as well as safer. And the sub-project called High Density Vertiplex. It's looking at the management of large volumes of traffic in the proximity of vertiport, handling these advanced eVTOL vehicles.
I want grandparents to be able to fly from one coast to another in 2 hours instead of 6, so they can visit the grandbabies. And when they get there, I want them to be able to get from the airport to the grandbaby's house in 15 minutes instead of 2 more hours. So we are developing the X-59 low boom flight demonstrator, and that flight demonstrator will demonstrate being able to fly over land at supersonic speeds without the loud crack, but a soft thump or not even perceivable. Now, what's important about that is not only do we have to do that here in the US, we're going to take this knowledge to the international organization such that this can be global, because that's what's going to make it an economic driver, not only for our nation, but for the planet. And we want to do that in a sustainable way. So we're working with our X-57. I talked about X-59. X-57 is leveraging electric propulsion. So what if all my airplanes could fly with renewable energy? That's a little bit far off, but we need to do the research now.
So the future of wind tunnel testing here at our facilities mainly is to test for noise, trying to reduce the noise signature of various types of airplanes. So the airplanes built 10 to 15 years from now will be so quiet that your conversation will be louder than the airplanes flying overhead. Besides testing those types of airplanes, we are maybe testing personalized airplanes. So we have to make sure that they're quiet enough to fly around cities houses and buildings. Working in the windowless, we get to see the future. We test the future. So the airplanes that we test here will probably be flying in the air in about 5 to 15 years from now.
Stvaranje tehnologije budućnosti nije lak zadatak. Taj proces traži mnogo predviđanja i testiranja.
The HIAD launches in a stowed configuration. And you can see behind me here an example of it, where inside that white cylinder, if you look through the holes, you can see that gold fabric. And that's actually a stowed HIAD. And this particular article, it's an engineering development unit that we're working on the ground to prepare for our flight test. And so this is our next launch of this HIAD technology. We've done a couple of launches, 2009 and 2012, where we demonstrated the concept of stowing this aeroshell inside a small rocket and deploying it. But those were what we call sounding rockets. They're suborbital vehicles, not a whole lot of energy. And so we ended up with a test that showed the concept worked, but we really didn't stress the system a lot.
In the cockpit motion facility, we have a single motion base that is a hexapod platform that can move the cockpit around to simulate the effects of aircraft motion. Individual cockpits themselves can be lifted on and off that platform through an overhead crane, which you may be able to see behind me. So the cockpits can be interchanged. We do a lot of the development work with the cockpit sitting off to the side of the facility in what we call fixed base mode. And when we're ready to collect data where motion effects are important, then we go ahead and put them on that motion base and run the study.
We're actually going to low Earth orbit with a primary payload that mounts on the top of this. We're flying with what's called the Joint Polar Satellite System, JPSS-2. We launch with them on a rocket out of Vandenberg Air Force Base with their payload mounted on top, and we're mounted in between them. The vehicle gets to an orbit, not the primary orbit, but an orbit, a parking orbit. And from that parking orbit, it then launches the primary payload to where it needs to be. And after that goes away, then we get deorbited by their second stage. And so their second stage actually puts us on a reentry path, and it aims us where we want to go. It spins us up to give us some gyroscopic stability that helps null out any issues we have during atmospheric entry. It's kind of a method we've used on capsules before. So now we're at this point, while we were still on that second stage, we inflated to the full shape. So this 1.5 meter diameter packed volume becomes a 6 meter diameter vehicle. And we're going to bring in about a little over a ton of stuff to demonstrate that we can bring back a large article. So this is 5 times as much mass as we've done before, and it's going to be 3 times the velocity. So it's going to be 3 times the heat flux, and it's going to be 10 times the heat load. So much more stressing case.
Clario Pathfinder is one of those instruments. Typically, for that long time scale, we need an overlap of instruments. Something like Clario, when we put up the full-scale instrument, will give us a NIST-level calibration source. So now I don't have to have the overlap, and I'll reduce my error bars around my data. So again, seeding the knowledge. As sea level rise happens, and here in Norfolk, some of the land is sinking, it'd be nice to know how that's going and what's driving that. So again, providing knowledge. So that happens here. We put the researcher, the scientist, the technician, and we complete that cycle. So the knowledge I want to capture and deliver, the measurement I want to make, how do I make that measurement, and how does that measurement feel knowledge?
So we're building Clario Pathfinder here on Earth, right? But we do want it to be orbiting around Earth so we can measure reflected sunlight globally. First, we need to make sure that we build the payload, so that's everything that is Clario Pathfinder. You can kind of see a 3D model that was printed by some folks here at NASA Langley sitting behind me. But it includes the instrument, it includes the pointing system that lets us look at the sun and the moon and the Earth at different angles. And we need to make sure that here on Earth, before we launch it into space, we test it in different ways. We test the different components. You start at the component level and you keep adding things on, and you kind of test as you go along. Once we put it on a rocket, and it won't be on its own ride, it'll be sharing a rocket with other things that will need to be launching into space or launching to the International Space Station. But we want to be sure that once we put it on the rocket and once it starts taking its measurements, it's performing in the way that we expect it to.
S napretkom tehnologije, znanja i razvojem komponenti, NASA može konstruirati uređaje kojima će se uzorci iz svemira dopremiti na Zemlju kako bi ih mogli dodatno istražiti.
Historically, we have done the robotic missions. And so those are missions where we send something to Mars. It's got a bunch of payload. It's got a payload that has a bunch of experiments on it. And we do those experiments and we send the data back to Earth, and that's the end. We're looking right now at sending something to Mars to bring back samples to Earth so that we can study them in a laboratory. Because you can imagine, if you've got, a laboratory or 100 laboratories or 1,000 laboratories around the world, if you had samples that you could share little bits with folks, you could do a lot more science than what we can pack on a small vehicle. Perseverance, which just landed on Mars, is caching the samples. So it's going around and finding the samples, and it's putting them in these little canisters and just dropping them along the way. And so we know where all the vials are at. And so the Mars sample return mission will actually send at what we call a fetch rover, which is a much smaller, less capable rover, just to go out and grab those samples and then bring them back to an ascent vehicle, which has what we call the orbiting sample container, the OS, and it will put all those samples in that, launch them into Mars orbit, and then that gets rendezvoused by an orbiter that's going to be built by Kinéis.
We're always pushing the boundaries of what can be done. We're trying to improve on what has been done before. So, for example, a novel thing about the Clario Pathfinder mission is that first, we're going to be taking highly accurate measurements of reflected sunlight off Earth. These measurements are important for us to observe the small but important changes in climate that we have been seeing and will likely continue to see. We want to make sure that we have objective measurements because humans, not the best measures of how much is something changing, right? We think about the weather that we experience day in, day out, and you can say, well, yeah, today's really hot. It may only be maybe in the 80s. Tomorrow it may be, 95 degrees Fahrenheit. You say, oh, it's hot, but it may not feel as hot to you. We're subjective beings. We want to make sure that our instruments are objective, and we want to make sure that they're taking highly accurate measurements of those small climate changes. The difference between climate and weather: climate is what you expect, weather is what you get. Weather fluctuates a whole lot more. So with what you expect, as that kind of drifts over time, you need high accurate measurements to detect those changes.
Razvoj nove tehnologije za zadaće s kojima se još nitko nije suočio vrlo je složen proces. Zato se NASA često udružuje s brojnim partnerima.
What's the art of the possible? What's that? I wonder if that's possible. So we allow our brilliant team to think out of the box. So it's not just Langley, you have these swim lanes, but somebody came up with a really bright idea. So we license our technologies. We partner with industry. We partner with universities to get those technologies out in the community. We publish books every year about all the NASA technologies.
We've got a lot of companies that are interested in using our technology to not just go to Mars, but companies are interested in reducing the cost of access to space. If we can get, stuff up in low Earth orbit and manufacture things in low Earth orbit, in that zero-G or near zero-G environment, we can do things that we can't do here on Earth. And so that's really attractive. But the two problems there are, one, you have to get all that stuff to orbit. And so that's how do you reduce the access to space? And the other problem is, okay, you manufacture this stuff in space to sell. Well, guess what? There's no customers in low Earth orbit. You've got to bring the stuff back here to Earth. The importance of this particular flight, by the way, is demonstrates some fairly large scale that starts addressing both the in-space manufacturing and low Earth orbit return, or bringing stuff back from space station, but it also helps us convince people that, yeah, we can do that low-cost access to space, bring back some of those assets. And coincidentally, a low Earth orbit entry at Earth, pretty close to what we get at Mars. So that makes it very attractive there.
The actual vehicle concepts or the vehicle models that we're simulating were developed by a sister project at NASA. They are reference configurations that have been developed so that there's no proprietary restrictions on how the data is being used. Those are developed through a combination of CFD modeling as well as for more mature configurations using some wind tunnel testing. Those are converted into math models that are compatible with real-time simulation. Along with that, we have other activities that are developing the flight controls. The flight controls interpret the commands that the pilot is making into their control inceptors and determining how the actual control effectors of the vehicle should move to match the pilot's desires. As well as we have other folks that are developing the display concepts. And you bring all those portions together and you basically have what goes into the simulation facility here and the various studies.
The International Space Station is a great resource. We have several instruments there, some that look at the sun, some that look at the Earth. Of course, we have astronauts on the space station. There's a lot involved with making sure our payload isn't putting any of the other payloads or the people on the space station in danger. So we're also working on that. And the payload, so Claria Pathfinder, will be installed on the space station robotically, and it'll be kind of connected to one part of the space station. So everyone kind of has their own home on the space station. So we have to know that ahead of time. That is an important piece of ensuring that our instrument works and behaves in the way that we need it to. It kind of goes both ways. No harm to our payload, no harm to the space station.
Langley je obogatio svijet za mnogo revolucionarnih inovacija. Što možemo očekivati u budućnosti i kako ćemo se vratiti s Marsa? To je problem koji znatno komplicira proces.
So what the future is planetary travel within our universe at the human scale. So we've done that robotically a lot, so now we want to get humans to Mars. So there's technologies we have to develop to get there. Our entry, descent, and landing expertise is key to that. It's not only structurally how I open it up, the materials that I need, but how do I deploy that? How do I do the simulators? We work with our colleagues to censor up a lot of the robotic landings so we can learn and leverage technologies going into the future. And when we do things like that, when we learn how to go from Earth to Mars, because right now with current technology, it's going to take several months, and then I have to wait for the planets to align. As I do that, how do I keep my crew safe? How do I keep my crew healthy? If they've been in space in microgravity for a long time, how functional are they going to be on Mars? So it's not just going to Mars and exploring, but that technology all comes back, because the same thing I need to do to keep my crew safe from radiation, my crew safe from whatever injury or thing that may befall, that applies right back here on home planet.
In the case of humans, and also in the case of sample return, now not only are we landing stuff on Mars, we've got to land the stuff to bring us back from Mars. And so that turns out to be a real challenge. You've got to land a lot more mass than we have before. And so that's one of the big motivators for this HIAC concept. In fact, in these in-house studies, we've looked at various technologies, and the only one that closes right now, the only one that lets us land the equivalent of a 3-story house on Mars, is this HIAC technology. And so getting that experience at from LEO at this 6-meter scale, and then getting further experience by bringing back assets from these rockets, which might require a 10-meter or 12-meter HIAC. And then that all builds to what we need to do for humans, which might be 18 meters in diameter. So 3 times the diameter, 10 times the size of this.
So all of our wind tunnel models that are tested inside the wind tunnel are designed and built so that they can withstand several times the expected wind tunnel load. So we rarely get a breakup or disaster in the tunnel, but every now and then we do. But most of the ones that have been dramatic are usually the helicopter models, because when they break, they break big time. It does get noisy every now and then. We do have protocols to make sure that we're the proper ear protection to make sure that we don't go deaf when we are done with the test.
What's really changed is that the technology has evolved to the point where some of those advanced ideas are at the point where both economically and practically can actually be implemented today. Looking ahead, 10, 20, 30 years ahead, I think what we'll be seeing with this area of advanced air mobility, which is the combination or the confluence of electric propulsion coming together with advanced automation technologies in smaller aircraft. We'll see things where aviation is much more closely integrated into our daily lives. So commuting by small aircraft may be a commonplace activity. It may not be an everyday thing, but a trip or two by week by small aircraft could become commonplace. Our cars serve us really well for making trips that are 10, maybe 20 miles long. Commercial aviation, large transports are great when we want to travel long distances, say 500 miles or longer. But there's this intermediate range travel on the range from 50 to 500 miles where nothing really works well for us today. Cars, of course, that's a multi-hour trip. And trying to use commercial aviation with a hub and spoke system, that's both, you've got to plan a long time in advance, as well as when you're changing airplanes through airports, the time savings compared to just driving can be limited. But the advanced air mobility concept is perfectly suited for those 50 to 500 mile long trips.
We're always discovering new terms that may impact the accuracy of our measurements. So that has certainly been a challenge. It's been a fun challenge. It's been great and reassuring to see, even though we have all of these uncertainty terms, we're still meeting our requirements to deliver this unprecedented accuracy measurement. This is important because we want Clario Pathfinder to serve as a reference. In addition to just taking its measurement of the climate system, we want it to serve as kind of an anchor or a reference to other satellite instruments that are also taking measurements of reflected sunlight. One instrument is not going to be able to do it all. Climate change is a global problem. It requires global solutions, right? So that's not just one team of people, as great as our team is. It needs to include other types of measurements, instruments that have different strengths, but we want to make sure that we can put them kind of all on the same playing field or all on the same scale. So the high accuracy measurements that we're working so hard to put together and we're working so hard to achieve will help us get to that place.
Traženje inovativnih rješenja na području istraživanja svemira zahtijeva mnogo vremena, resursa I testiranja da bi dalo plod.
So our history has been a cadence of we do ground-based testing to develop what's going to be tested on the next flight test. And then we do that, and then we go back to ground testing. So we first started from the ground, the ground floor and just saying what materials are out there off the shelf that we might be able to use and how would they perform. And so we did the temperature tests on them and put airflow across them just to see if they would even hold up to the shear layer that you get as the flow goes across the surface. So we weeded that kind of stuff out and said, okay, well, where can we test this? And so we flew it on the sounding rockets at the small scale. That was at 3 meter scale, so half the scale that we're getting ready to fly with this vehicle back here. Then we went back to the ground testing and said, okay, well, what's it going to take us to get from 3 meters to 6 meters? Now all of a sudden, these are not small bundles of things that we can just carry with a couple of people. We've got to now have cranes, and we've got to have special fixtures to manipulate this and all those kind of things. And so we did all that work to build up to this. And now we're flying this, and then the next thing would be, okay, now if we need to get to 12 meters, what do we do? And so the near-term interest is we're going to start working with these companies that are willing to fly it with a little bit higher risk than we would want to do for a multi-billion-dollar mission to Mars. And so, like SpaceX, these companies are willing to just say, hey, we're launching anyway. As long as it doesn't interfere with us delivering our primary payload, we can just try stuff. And so with that mentality, we can just put a HIAD on one of these rockets and just test it that way.
It's funny, you go to a party and you tell people that you work at NASA, and things that you kind of get glazed over. I think everything that you do on a daily basis loses some of the shine, but when you get the opportunity to tell other people what you do, they help you remember just how exciting some of it is. In this facility here, I've done studies looking at spacecraft handling qualities, simulating docking missions with astronauts to the International Space Station. I've worked on transport aircraft, and now working on these advanced air mobility vehicles. So a lot of exciting things.
I'm excited to see how folks are going to connect this picture that we're making with Claria Pathfinder to other pieces of the puzzle. What's the full picture going to look like? How is that picture going to evolve? I'm just kind of one piece of this whole big picture, but we have new scientists coming into the field every day. I love talking to students and kind of getting them excited about science, showing them what scientists can look like, and showing them that, hey, they can do this too. If you have an interest, it can start from a fear of thunderstorms, and it can evolve into having a broader impact on the climate science community.
My very first day, I spent with a classroom full of 3-year-olds and 4-year-olds. The 4-year-olds, we made a solar system. I was the sun, they were the planets, and we spun and we revolved and we laughed and we joked. And then we talked about the solar system, and the 4-year-olds could tell me about the smallest planet, the largest planet, the hottest planet, the coldest planet. Not because I put equations on the board or asked them to memorize, because we experienced it. Then I talked to 3-year-olds about gravity, aerothermodynamics, coding, and engineering. Yes, I said 3-year-olds. And then I held a ball in my hand and I dropped it. And I asked, why did the ball fall? And a 3-year-old, she told me because it's not a balloon. And then she told me why a balloon goes up. So imagine the amazing she's gonna do, her peers are gonna do. We need all those bright minds that come and do this thing we do. Everything we enjoy today is because somebody put the work in 5, 10, 15, 20, 30 years ago. Imagine what that 3-year-old's gonna do. I tell people that for whatever, I had breakfast in Seattle, Washington one day, and dinner the same day in Washington, D.C., and none of us give that a second thought. But there was a time when that would have been magic, right? Imagine what's gonna be magic in 5 years and 10 years. That's what we do at NASA, and that's what we do at Langley.
Stručni timovi iz Istraživačkog centra Langley s mnogo ljubavi i strasti pristupaju svom poslu, koji ih neprestano usmjerava prema revolucionarnim inovacijama. Pred njima je dug i težak put na Mjesec, zatim još dalje, na Mars i na posljedku povratak na Zemlju. U sljedećem nastavku predstavit ćemo još jedan NASIN centar.